we are discussing how to synthesize an op-amp, and the first goal is to have a circuit that is sensitive to the difference of two voltages. Okay, that is everything. A voltage is always a potential difference between 2 points, but here we are talking about having a common ground, two voltages with respect to the common ground, and the circuit should only react to the difference between those voltages. Okay. So, we want something of this sort, where this is V1 with respect to ground, V2 with respect to ground, and we should have a current that is proportional to V1 minus V2. Okay. I mean, this symbol is nothing but a voltage controlled current source. Okay. This is some GM times V1 minus V2. That is what we want. And since we have a transistor which is a voltage controlled current source, and the voltage controlled current source responds to the voltage difference between gate and source. So, in the incremental picture, we could think of having something of this sort, where at the gate you have V1. Again, this is the incremental picture. We have to take care of biasing. For now, assume that it is biased in saturation. V2, if we do this, the current here will be the GM of the transistor times V1 minus V2. But the problem here, of course, is that here we have infinite input resistance, whereas here we have a very small input resistance of 1 by GM. So, unless when the voltage sources V1 and V2 are non-ideal, which they will be, we will not have an ideal voltage source ever, we will not get GM times V1 minus V2. Okay. So, we will get GM times V1 minus some number which is smaller than GM times V2. Okay. So, now we know that if we have a heavy load, that is a small RL, and we have to drive it from a non-ideal source which has a relatively large resistance, the known solution is to use a voltage buffer. Okay. Otherwise, you would have got an attenuation RL by RS parallel RL, you would have got a ratio of output to input, which is that. And if RL is much smaller than RS, that number will be very small. So, very little of the input Vi actually reaches the load, but with a voltage buffer almost all of it can reach the load. So, we will try that solution. We already found some transistor circuit which will act as a voltage buffer, and that is the source follower, okay, or the common drain amplifier. How does that work? You have to apply V2, the voltage that you want to buffer, to the gate of the MOS transistor. Again, all this is just incremental picture. The drain is not used, it is grounded, and in this case at the source you will get something nearly equal to V2. If you do have a load, you will get GMRL by 1 plus GMRL times V2, and you have to make sure that GM is much more than 1 by RL. Okay. So, we have some buffer. So, the next thing to try is now this is the, let me label the transistors also. M1 is what I think of as the amplifier transistor, and M2 is the voltage buffer. Okay. So, I have my M1 here, and I had to apply V2 to this point, but I will apply it through a buffer M2. Okay. Again, we are still in the incremental domain. So, I have not yet connected anything to the drains of the transistors. So, my first goal is to get a current that is proportional to the difference V 1 minus V 2. Okay. So, I will connect it up like this. Now, we know that we have to go through further analysis, because first of all, this is not an ideal buffer. It will have an output resistance that is not 0. It will have some non-zero output resistance and so on. Okay. So, we have to analyze this, and in the simplest model, I will assume I will model M1 with the transconductance GM1 and M2 with the transconductance GM2, and I will not worry about the output conductances for now. Okay. If we carry out this analysis, which you did yesterday, so I will have V1 here, RS, this is GM1 times the voltage difference between these two. Okay. So, let me label this incremental node voltage as Vs. So, across this we will have V1 minus Vs. Okay. And across this we will have V2 minus Vs, where this is V2. Okay. And this is incrementally open circuited here, right? There is no current flowing out this way. So, the current here, which is GM1 times V1 minus Vs, should be equal to the current this way, which is GM2 times Vs minus V2. Okay. And from this you can solve for Vs. What will it turn out to be? What is it? Yeah, it is some linear combination of V1 and V2. Okay. And then what are these currents? If I call that ID, what is that? GM1, GM2 by GM1 plus GM2 times V1 minus V2. No, right now I just want to get a current which is proportional to V1 minus V2. Later I will use that current in something. I mean, I will pass that current through a load or do whatever is required. Okay. So, it turns out that this, in spite of the non-ideal features that we did not, I mean, in the initial synthesis we just said, hey, we will throw in a buffer. In spite of that buffer being non-ideal, it does work as originally thought. It will amplify the difference V1 minus V2. Okay. And the proportionality constant is not Gm of M1 or M2, it is some combination of the two. Okay. So, now first of all I assumed different GMs for this and that. Again, that is not necessary, we can make it before that. Now, originally I thought of M1 as the amplifier, and I applied V1 to the gate and I applied buffered V2 to the source. Okay. But if you look at the structure the way I have drawn it, it looks exactly the same. If I had originally thought M2 as the amplifier, thought of M2 as the amplifier, applied V2 to its gate and applied buffered V1 to the source. Okay. So, this circuit, the topology, the picture is symmetrical with respect to V1 and V2. Okay. What is not symmetrical is the values GM1 and GM2 I assumed in general to be different, but we can make it exactly symmetrical by setting GM1 to be equal to GM2. Okay. So, let me make GM2 equal to GM1, then what will be the voltage here? This voltage, it will be the average of V1 and V2. Okay. And what is the current ID? GM1 by 2 times V1 minus V2. Okay. It is just half of the GM of the individual transistors, that is all. Okay. So, now we have actually a symmetrical structure for the two inputs, and this is exactly what we were looking for in the first place. Okay. We want V1 minus V2, and the circuit shouldn't kind of distinguish between V1 and V2. It should just give you the difference, it should give you a current that is proportional to the difference between V1 and V2. This is okay? Any questions about this circuit? To make it them symmetric. Yeah, I mean, I want it to behave the same way from V1 and V2. Okay, I want the circuit to look the same, right? Initially, it was arbitrary. I had applied V1 to the gate of M1 and V2 to the source of M1. Okay, and I buffered V2 and applied it to the source of M1. Now, if I look at this circuit, I could equally well have started from V2 being applied to the gate of M2 and buffered V1 applied to the source of M1, M2. Okay. So, essentially the picture is symmetric. There is no reason to think of V1 as the first input and V2 as the second input and so on. So, I want to make everything symmetrical, I will use it. Yeah. So, there are some practical problems that will come up. Okay. So, now we have chosen a model in which we have ignored the output conductance and all these things. So, the best result will be obtained when we have identical transistors, okay, which are biased identical. Any other questions? Keeping? There is, we will see. I mean, after we introduce the bias, you can, there may be some use. Most of the times it is not used that way, but you could think of some things. Any other questions? So, this structure which amplifies the difference V1 and V2, we have to add the bias to it. So, this is not the complete picture yet. So, this is known as the differential pair. Okay. Differential pair is just these two transistors connected at the source, and here we have an open circuit in the incremental picture, that is no current flows out of this. Whatever current flows from drain to source of M1 has to flow from source to drain of M2. Okay. So, that is an essential property of the differential pair, right. And this node which is common, this is the, because the two sources are connected together, this is, I mean, many times these terms do not make any sense, but this is known as the source coupled node, or more often just the tail node. Okay. So, we see that if GM1 and GM2 are identical, right, the tail node voltage is simply the average of V1 and V2. Okay. Any questions about this? Now, this is of course incomplete. I mean, this is the picture we want to have as the incremental picture. We have to now come up with appropriate biasing for this, right.